Today I am going to discuss with you quantum numbers. The modern periodic table is based on quantum numbers. S, P, D, F, N, M, L, S. All these are quantum numbers. What they are, how we arrived at them. In a nutshell, we are going to discuss all these things backed up with a few problems at the end to enrich your understanding of this part of atomic structure. I've been away from producing videos on atomic structure because of some preoccupations, but now I'm finally back at it. So let us discuss quantum numbers. The basic concepts of quantum mechanics. Electrons exist in areas outside the nucleus. These areas are called energy levels. You might have heard of them before as shells or orbits. There are numerous energy levels at which the electron can be found, each at a progressive higher energy. As the distance from the nucleus increases outwards, the energy of the electron residing in that orbit also goes on increasing. The closer the electron is to the nucleus, the lower is its energy, and the farther away it is from the nucleus, the higher is its energy. These levels are assigned numbers 1, 2, 3. They can be assigned up to infinity, but we go only up to 7. As the number increases, the energy state of the electron becomes higher, as explained just before. Now, basic concepts of quantum mechanics. The original atomic theory proposed by Niels Bohr in the earlier 20th century suggested that electrons circle the nucleus of atoms in orbits similar to paths of the planets around the sun, the planetary model. Rutherford, as explained earlier in the previous video, was able to locate the nucleus and the entire matter possessed by it, because it was hard, dense, and positively charged. So positive charge were residing inside the nucleus, and that's what he said. But he did not give any particular region in the atomic volume to the electron. He just said that electrons are externally found in extra nuclear space. Bohr was able to fix this problem, and he said that they revolved around the nucleus in closed orbits at particular distances, and while moving, they neither gave any energy nor absorbed any energy. And so that explained the stability of all the atoms. The most important concept of modern quantum theory is, however, that electrons do not move in orbits about the nucleus of the atom. The energy levels of atoms are not orbits for electrons, they are areas of high probability of finding electrons. Therefore, you see, there is a big leap from the planetary model, which has been taught to you since 7, 8, 9, 10, even to 11. But now the concept is about to change. There are areas around the nucleus, close to it, where there is high probability of finding an electron. That area is known as orbital. So electron spends most of its time in that orbital. This is Bohr's planetary model, and you can see that there is a nucleus which is positively charged here. The positively charged nucleus shown by the plus sign here, around which we have circular orbits 1, 2, and 3. We count the orbits from close to the nucleus outwards. So this is 1, this is 2, this is 3. I can write it also. This is 1, this is 2, and this is 3. This is also known as K, L, and this is M. But what I'm about to explain to you is something different. Bohr was able to find the energy of electrons. Now, but his model was only applicable to hydrogen. Now let's see why it was applicable only to hydrogen. These two electrons are orbiting in the first shell, which is at the same distance from the nucleus, which means both these electrons must have same amount of energies. But the emission spectra showed a different picture, which means both these electrons may be at the same distance, within the same distance from the nucleus, but they are not equally far. And that's why the energies are different. Therefore, this model fails. According to this model, all these 8 electrons orbiting in the second shell, or the L shell, as I have named it here, they must have same energies. But that is not the case. When spectral lines are passed through magnetic field or electrical field, Zeeman and Stark effect that you must have learned, they split up into fine lines which are very closely spaced, which means the energy of these electrons as they are in this gap, all electrons will not have equal energies, but they will have different energies here because the spacing is not equal. There are areas of high probability where these electrons can be found around the nucleus. Therefore, the picture was all set to change. Now, what we have been lacking in introducing here is the wave nature of electron. So far, you see, till 1808 and even in 1895, the atom was a solid sphere. It could not be divided into anything. But soon we saw that there were electrons. Close on the heels of this came the protons and the neutrons in the nucleus. And this model was developed by Bohr, but applicable only to hydrogen. They're small subatomic particles. When they move, they have considerable waves associated with them. So unless we take into account the waves associated with the electrons, we will not be able to find or come to a conclusion about any proper model of an atom. Now, de Broglie's hypothesis of wave-particle duality and Heisenberg's principle of uncertainty, del x into del p equals or more than h by 2 pi, and Schrodinger's wave equation finally gave an uncertain, a probabilistic picture of an atom, where there are probabilities. Here there are certainties. These certainties are not there. The electrons, these 8 electrons, can exist anywhere between this outer side of this black line to the inner side of this black line, but all of them are not on this line. And that is what exactly it means. Now, this model is a probabilistic model. So you can see that the electrons are no longer given the arrangement on this line. It is below this line within this region. You see, this is slightly below, this is more inside, this is in the middle, and so on with these two electrons also. So the deterministic picture has been replaced by a probabilistic model where probabilities are there. Now, using our knowledge of light to understand electronic structures in atoms, recall from our previous information, when atoms absorb energy, electrons jump to higher levels. When they fall back to their original energy levels, that absorbed energy is released as light, light of one particular wavelength. That is why in emission spectra you have sharp lines. The rest of the energies are missing. Analyzing this emitted light allows us to discover the electronic structure of the atom. So there is no direct viewing of the sequences that are in the atom. We have to interpret the data which is given by the emitted light by an atom. Before we can do this, however, we must first investigate the second nature of light, that is its particle nature. As I just mentioned, de Broglie was the scientist who linked wave particle duality. He said, well, if waves can behave as particles, particles must have waves when they move. So that is wave particle duality. Light particles, Planck and photons. Particles of light are called photons. These are packages of light energy. A photon is a small packet of light energy. Max Planck was first to discover the relationship between the wave nature of light and its particle nature. He found that energy content of light was directly related to the frequency of the light wave. The equation that measures energy as a function of frequency is energy equals a constant into frequency. And this, you see, is written as, E equals H into, this letter is pronounced nu. It is pronounced as nu. This letter is pronounced as nu, N-U. And this stands for frequency, and this H is a constant known as Planck's constant. So E equals H into nu, where H is a constant called Planck's constant. And this is Mr. Planck. And the value is 6.6 into 10 to the power minus 34 joule seconds per photon. In addition to light, very high velocity subatomic particles such as electrons also have observable wave properties, as I mentioned earlier. We cannot neglect them. The wavelength of these particles can be calculated using de Broglie's equation. It is written de Broglie, but the spelling is that, but the French scientist, it is pronounced de Broglie. Lambda is equal to h by p, or p is equal to m into v. That is momentum of the particle. So you can see that the wave nature here and the mass is here, and both are interrelated. According to de Broglie's equation, lambda equals h by p, mv is equal to p, and mass into velocity is p, which is momentum. Where h, Planck's constant, is 6.63 or 6.6 into 10 to the power minus 34 joule second per photon. M is in kilograms. V, velocity of the wave, is in meters per second. And this is de Broglie, and aptly said, if you are moving, you are waving. Now, sample problem. All moving objects have wavelengths, even everyday objects. However, large mass particles exhibit very short wavelengths which cannot be measured by the instruments in use nowadays. And that's why they are meaningless. Something which cannot be measured is meaningless, as we shall see. For example, what is the wavelength of a 60 kg runner who is moving at 10 meters per second? So let us apply the equation and find out. So the wavelength lambda is equal to h divided by m into v. Lambda is equal to h. The value of h is 6.63 into 10 to the power minus 34. We haven't taken into account the units here. Divided by 60, which is m. The value of m is 60, and 10 meters per second is the velocity. So that is momentum. And it comes to 1.11 into 10 to the power minus 36 meters. Now this is too small to be measured by any equipment in use for measuring a length. And that is why it is meaningless. A very, very small wavelength. It cannot be measured for very small masses, electrons. Now, a very, very small wavelength, for very small masses, electrons, the wavelengths are quite significantly larger, and therefore they can be measured. Now, something which can be measured and is associated with some type of matter cannot be neglected. So what are quantum numbers? Now, quantum numbers are obtained upon solving Schrodinger's wave equation, which is given later, for a particular electron of particular energy, and it gives many values. And some of the values cannot be entertained. Only the reasonable values which are entertained are used for finding out the address of an electron in an atomic system. So quantum numbers are nothing but they give you the address of electron. They define the electron separately from all others. numbers are a set of four values that define the energy state of an electron in an atom. Quantum number values are designated as N, L, M, and S. S is often written as MS. That is spin quantum number. N is called principal quantum number and ranges from 1, 2, 3, etc. Also refers, theoretically it can go up to infinity, but we go only up to 7 because the periodic table does not have more than 7 periods. That means the seventh orbit is the last orbit which is getting filled, or seventh energy level is the last energy level that is getting filled. L represents the orbital type and depends on N. It ranges from 0 through N minus L. It is often called the azimuthal quantum number. M depends on L. It ranges from minus value of L through 0 to plus L value. It defines the orbital orientation in space and is called the magnetic quantum number. S is the spin quantum number or the spin number. It is either plus half or minus half. Plus half clockwise spin, minus half anti-clockwise spin of the electron. Now, assigning quantum numbers to different atoms and different electrons in different atoms, the quantum numbers may be viewed as an electron address, the address of electron, as I said earlier. Just like your address, each has its own distinct set of values. So no two electrons can have all four values of all four quantum numbers identical. Even in the first shell, we have two electrons. The spin is going to be different. For one electron which is spinning in a clockwise manner will have plus half value. The other electron will then have minus half value, because electrons pair up with anti-spin. For example, in order to receive a letter, the address must contain the state, the zip, city, street, and name. No other person has the exact same set of information. It is similar for electrons. They each have their own address in terms of N, L, M, and S. If N, L, M are equal, S will be different for two electrons, which means no two electrons have same energies. No two electrons in an atom can have exact same set of quantum numbers, which would mean that if this were to be, then two electrons would have same energies, but it is not the case. So no two electrons in an atom can have the exact same set of quantum numbers. Quantum numbers are assigned to each electron using the rules previously stated, starting from lowest value, where n equals 1. The Schrodinger's wave equation that I talked of is this. It's a second degree differential equation, and it gives you two things, you see, the energy and psi. And there is another term called psi square. Psi, the value of psi indicates the orbital, the probability, or psi square indicates the probability of finding an electron in a given space. whereas psi tells us about the space and its shape. Different quantum numbers, this is already explained, so no need of going into it. Assigning quantum numbers to atoms. So we keep the atom here along with its atomic number, because atomic number gives us the number of electrons also. Atomic number is the number of protons, and in a neutral atom, the number of protons and number of electrons are equal. So atomic number gives us the number of electrons present in an atom. And then we have N, L, M, and S. Let us see. Hydrogen, which has only one electron, will have N value 1 because it is going into the first shell. Lowest possible value for N is 1. L for N equals 1 is 0, because the value of L starts from 0 and goes up to N minus 1. So N minus 1, 1 minus 1 is also 0. M, which starts from minus L through 0 to plus L, here L is equal to 0, and therefore we can have only one value of M, and that is M equals 0, because minus 0 through 0 to plus 0 is meaningless, not mathematically entertainable. That one electron will have minus half spin, so they have taken it as clockwise spin, so minus half. And therefore, for one electron, we have the N, L, M, and S values as 1, 0, 0, and minus half. In some books, plus half is taken first. Let us take another example. So this time we can use the same N, L, and M values as the first electron and still get a different set of values by changing S to plus half. Energy level L is now complete. We are at the end of period row 1 on the periodic table. So atomic structure is the basis of the formation of the new periodic table or the modern periodic table. Helium with 2 electrons. N equals 1, L equals 0 for this electron, M equals also 0, S is minus half for the first electron, second electron, again N equals 1, L will be 0 because N minus L is 0, 1 minus 1 is 0. M will be 0 again, because if you have L equals 0 and the value of M depends upon L, so we cannot have plus 0 through 0 to minus 0, which is meaningless, so it cannot be, and therefore its value is also 0. For second electron, M is also 0, and here there's a change. So the first one was given minus half, this electron will be given plus half, and the two electrons with opposite spin pair together. Now lithium. This time we must change to n equals 2. Otherwise, we will duplicate the first or second set of numbers. Following the rules, we get the set shown. Notice that we change n again, start at the lowest possible values for L, M, and S. So 100 minus half, 100 plus half, and in the second shell there is one electron. So 200 and minus half. There are three electrons, so there are three possible set of quantum numbers. None of them match exactly. Beryllium, four electrons, so there will be four sets, one and one as in the case of helium, two as in the case of lithium, and the fourth electron is shown here. So 2 L is equal to 0, N is equal to 0, and this is, if the first one was minus half, this is plus half. This time we can use the same N, L, M values as the third electron and still get a different set of values by changing S to plus half. So S has been changed here to plus half. Now boron, the fifth, the fifth electron. These four sets are the same as in the previous boron 4e, but for beryllium 4e, but boron, the fifth electron which enters the second shell, is now going to another set of orbitals. L equals 0 means s orbital. L equals 0 is s orbital. So here we enter S as 1, here S2 gets completed, so 1s2, there are only 2 electrons in the first shell, K shell. Then 2 electrons again enter into 2s. These are 1s, 1s1, 1s2, this is 2s1, 2s2. So the third electron, which is entering in the second shell, is now going to p orbital. This is 1. So we start with minus 1. M is minus 1, then comes 0, and then comes plus 1. So let us see. But in boron, this is the quantum number values of the last electron that enters it. N equals 7. Now let's see. So we have, in the second shell, we have seen by application of Bohr-Bury formula, that is 2n square, 2n square for second shell will be 2 into 4, 2 into 2 square, which is 8. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So 8 electrons are shown here, where n is only up to 7. So we are seeing this one. Now, we saw in boron 5, The value of this was -1, this was -12. When the second electron comes, it goes to again a new orbital. Ohm's rule of maximum multiplicity is followed here. There are three p orbitals. There are three p orbitals known as px, py, and pz. Any orbital can have only two electrons, one with minus spin and one with plus spin, both cancelling each other and stabilizing the atom. So when we saw this yellow line here, beginning from here, this was the fifth electron in boron 5. L is 1, -1, -12. Then it goes to another orbital. Its value is 0, which is in py, and then it is again -12. Then it goes to the third orbital, that is pz. The value is +1, and again it is -12. Now when the pairing begins, then we have +12, +12. So this +12 actually pairs with this one. Another +12 will pair with this one, and the last +12 will pair with this one. So p orbital will have 2, 2, and 2, a total of 6 electrons, of which only 4 are shown here. Now the quantum number summary. If m equals 1, L equals 0, m equals 0, S may be +12 or -12. N equals 2, L equals 0, and then L equals 1. L equals 0 means S orbital, L equals 1 means p orbital. That means the second shell harbors S and p orbitals. The total number of electrons for p orbitals, because there are 3 different orientations, will be 6. As I said, any orbital can have only 2 electrons, one with positive spin and other with negative spin, cancelling the spin momentum of each other and stabilizing the atom. M will be, for L equals 0, M will be 0. For L equals 1, M will be -L, 0 plus L. S again will be +12 or -12. N equals 3, that is the third shell. Here we can have possibly S orbital, p orbital, and this is d orbital. For L equals 1, these are the 3 values, so px, py, and pz. For L2, m is given here from -L to +L through 0. So -2, -1, 0, +1, +2, with S being either +12 or -12. In the fourth shell, we can have 4 different orbitals. L equals 0, L equals 1, L equals 2. So S orbital, p orbital, d orbital, and it opens the gate for the f orbital also. So the values of m for L equals 3 will be -3 through 0 to +3. So that is, you see, 7 different values. So 7 different orientations are there for L equals 3. F orbital has 7 different orientations around the nucleus. M has 5 different orientations. Now, F9, you can try yourself and you will arrive at these numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. In the ninth, you see the pairing up takes place here. So there is only one electron which is unpaired. This electron remains unpaired because this pairs with this pairs with this pairs with this, and this is unpaired electron in fluorine, unpaired. And what fluorine does is it tries to take an electron from some other element and get this electron paired and obtain the structure of the nearest noble gas, which is neon. So translation from spectroscopic notation to quantum numbers. For larger atoms, the assignment of quantum numbers must continue following the rules until the number of electrons corresponding to that particular atom is reached. As we have done in the case of fluorine, we started with hydrogen, then we went to helium, then we saw lithium, and so on up to fluorine. In the middle, we missed carbon and oxygen. We didn't do that. But it is left as an exercise for you. For larger atom, writing the quantum number for a particular electron can be made easier by translation of spectroscopic notation into a quantum number set. So this is a spectroscopic notation. This is a spectroscopic notation 4s2. This means that in the fourth shell, n equals 4, and s means L equals 0, and therefore m must be 0, s can be minus half or plus half. 3p is a spectroscopic notation and can be translated as follows, or can be understood as follows: n equals 3. So this 3 signifies the major energy level, that is shell number 3. P means L equals 1, as we have seen in the previous slide in the summary, and therefore m must be minus 1, 0, or plus 1. And s, always you say we have minus half and plus half. So when I write minus L, one electron here with minus half and one electron here with plus half. So this is minus L and this is there. In 0 also, one electron will be here minus half, another electron here plus half, and in plus 1, in plus L, again another electron here with minus half, and it will get paired with another electron here with plus half. That brings us to the end. I hope you have enjoyed learning. Do practice, please, and comment and put forward your difficulties to be solved in upcoming videos. Thank you and have a nice day and nice learning. Bye.